Hey guys, welcome to the next Diels Alder video. So in this one, we're going to be covering what happens if you have a cyclic dienophile. In the previous video, we covered how do you do Diels Alder with cyclic dienes, right? We got like those 3D ring structures, so just always watch out for that. Now we're going to look at how we do it with a cyclic dienophile. It's exactly the same thing as everything you've been doing. There's only one special thing that I want to mention about these things that throw a lot of people off. And so to do that, we'll go through this problem. All right, so let's get started. So we have our dienophile and we have our diene. Now notice the diene is in the S-trans conformation. Diels Alder is always in S-cis, so we need to redraw this. All right, so here's our diene like they gave us, right? You can see that the double bonds, right? We want to get this to have that double bond to face the same side as this one, right? So I'm going to just divide this guy in half and flip one end of the molecule. It doesn't matter which one you want to do. I'm just going to pick this one. All right, and so that's how it's going to look. So here's our diene. Now I'm going to redraw our dienophile, and I'm going to also reorient the diene itself. Make sure to pay attention. You see that there's this methyl here. It's pointing outwards. So when you redraw this diene, you want to have it pointing outwards. And now our dienophile is right here. Okay? So these are going to be our reactants in the Diels-Alder reaction. Now we got to find a product. Okay? So let's see. Remember, in the first step in the Diels-Alder is the Regio Chemistry, right? Where's that partial positive and negative? So let's draw some resonance structures. If you look on the diene, we have this methyl group, right? That is an electron donating group. So remember, it doesn't have resonance, but we're going to pretend like it does to help us better visualize it. So I'm going to put a lone pair here, right? Remember, there isn't actually a lone pair, just to pretend. Bring it down in the form of a double bond. That's going to push this double bond over here, and that's going to put a lone pair in that carbon, giving us something that looks like this. Negative charge here, double bond there, and here's our fake double bond, right? But the important part is that we know that this carbon has that partial negative, all right? So I'm going to just highlight that carbon, partial negative. Now let's look at our dienophile. Our withdrawing group is going to be this carbonyl, right? Because I can draw a resonance structure taking this double bond up and bringing that carbonyl double bond up, giving us something that looks like this. O minus, double bond, and now this carbon doesn't have a full octet, so it gets a positive charge. So what's important is we found the carbon with a partial positive. So I'm going to highlight it blue, partial positive. Okay? Just to keep track. So we know how, now we know that the negative carbon has to attach to the positive carbon. Alright? So let's, before we go any further, number our structure. 1, 2, 3, 4, 5, 6. I'm not going to number the rest of it. I just prefer to number only the carbons that are going to be part of the Diels-Alder ring itself. Alright? So let's draw our 6-membered ring. 1, 2, 3, 4, 5, 6. We know the double bond is going to form between 2 and 3. Carbon 1 had a methyl. And now 6 and 5, let me just move the numbering, right? If I finish off that numbering, but I'll do it in, let's say, A, B, C, right? So we see that off of carbon 6 is carbon A, right? So here's A. A was connected to B. B was connected to C. And C was connected to carbon 5. We also know that carbon A had the carbonyl, so let's put that over there. All right? And so that's the product of the Diels-Alder without stereochem. All right? We have the Regio Chemistry perfect. the one thing we have to now do is the stereochem. So let me just actually erase the numbering to make it a little bit easier. All right. So we have the Regio Chem. Let's just focus on stereochemistry. All right. So remember, we want to have the groups pointing outward, right? Like this group, to have the same stereochemistry as the electron withdrawing group. Okay. So let's see. And also remember that we always have to maintain stereochemistry. This dienophile, right? Because it's a ring, there's two hydrogens coming off of it. They have the same stereochemistry, right? This part of the ring has its will also have the same stereochemistry, but you may be wondering, there's double bonds there. Why would we have stereochem? But remember, the double bond gets removed over here. All right, so there's still two hydrogens, right? And like we said, they're going to have the same stereochem. So now, these are our choices, right? So remember, we want to have the same stereochemistry for our electron withdrawing group as these trans groups, right? So let's say I make it wedged. All right, so now we need to make our electron withdrawing group the same thing. It needs to be wedged. So you may think, all right, so let's just go like this, right? And you'd be right. The only problem is, if you look at the choices, we don't have any stereochemistry on these bonds right here. And there's a reason for that, just because it's a little bit difficult when you have rings like this, right? And let's say you have this other 6-member ring that looks something like this, right? If we want to show that that ring is kind of pointing downward, right, into our page, it's a little bit annoying and harder to see when we have bonds like that, all right? Or if I drew a wedge like this, right? So what we do instead is we assign the stereochem to the, we assign the stereochemistry to the hydrogens. So let's think about this for a second. This can get a little bit tricky, but if you take it step by step, you'll understand it. Let's look at our dienophile. Let me erase this. All right. We said that these hydrogens, right, they're going to have the same stereochem. That means these bonds right here have the same stereochemistry, right? So the hydrogens will have opposite stereochemistry. Those red hydrogens will have opposite stereochemistry of the purple bond. So we know that we want to make our purple bond wedged. So you make the hydrogen dashed. Okay. And because this hydrogen at the top was dashed, and this hydrogen is supposed to have the same stereochemistry as it, we'll make that dashed as well. All right, and so that's going to be our answer to this question. It's going to be choice B. So you see that the reason I wanted to show how we do these problems is to introduce this idea that we can, when you have multiple rings in your Diels Alder, more often than not, you'll see that the stereochemistry is given to the hydrogens. So just pay attention. This stereochemistry of the hydrogen represents the opposite stereochemistry of this. If that hydrogen is dashed, this bond is wedged. If the hydrogen is wedged, then this bond is dashed. All right. So I just want you to keep this in mind. Now, one other thing I do want to mention, other than the cyclic diene and dienophile thing, is a special case with the Diels Alder that you guys may see. All right. We can do Diels Alder with triple bond dienophiles. All right. So this is something to just watch out for. So here's our triple bond, right? And remember the carbons are, there's 2 carbons there and 2 carbons there, all right? The arrows work the exact same way. You're going to draw that ring. And let me just number the carbons too. 1, 2, 3, 4, 5, 6. 5 and 6 are the carbons part of that triple bond. 1, 2, 3, 4, 5, 6. All right. So carbons 2 and 3 get the double bond. Now, remember when we had a dienophile, right? So if when we had the normal dienophile, we had one double bond there. And that one double bond made that connection between carbon 4 and 5, right? But in this case, you can think about it, the triple bond has 2 double bonds. So while one is used to connect 4 and 5, we still have one left over. So we have that double bond left over here. And you're going to just put COOH, COOH, no stereochemistry, because they're on carbons with double bonds. So just watch out for this, all right? When you have a triple bond, you're going to still have one double bond left over. You'll see this a lot in terms of when they give you the product of the Diels Alder and they ask you to work backwards and find the reactants. And don't worry, I'll make a video on how we do that as well. All right? I'll see you guys in the next video. Hope this helped.